Thank you, Ihor. Yeah, thanks for coming to this deep dive session on structured streaming. Today we're going to talk a lot about the basics of structured streaming, some details on some of the newest features, and then we're going to close with some actual use cases about how we use structured streaming internally at Databricks. So just as a little bit of introduction, I want to start by just kind of talking a little bit about Databricks. So we were founded initially by the team that started the Apache Spark project, and our mission is to make big data simple. And the way that we kind of try to achieve that is we have this online platform where users can log in, start Spark clusters, and actually run commands and get the results back. But what that kind of means to you is we're running this large cloud service. And one of the things that we use to manage this cloud service is structured streaming. And so we'll be going into a bunch of the details about how we do that. But before we go, let's kind of start a little bit by talking about why we started the structured streaming project and what our goals were with it. So we started this about a year ago. And at the time, what we realized was that building robust stream processing apps that return the correct answers and integrate with other systems was very difficult. And in particular, there's kind of three things that make this difficult. So starting off, just the data itself is complex. So it often comes in a bunch of different formats. I need to parse JSON, I need to parse Avro, I need to work with binary data. And additionally, the data itself can be very dirty. So you get late data, you get out of order data, you get duplicates and things like that. And with this messy, complex data, I actually have a bunch of different workloads that I want to perform. So some of them are streaming, some of them are ETL. Sometimes I even just want to be able to do ad hoc interactive queries. And in more advanced cases, I even want to be able to take machine learning, train models, and then use those models inside of my stream. And then finally, the really hard part here is we're always running this in a distributed system, and we're connecting to a diverse set of kind of external systems, both as input and as output. So we want to talk to Kafka or Kinesis, we want to interface with S3, and we want to do all of this in the presence of system failures, while still running a 24/7 highly reliable stream. And so doing this can be pretty difficult. So when we created the project, we started with a bunch of ideas. One was that we wanted to take all of the nice things that users liked about Spark SQL and make that available as streaming. So this is both the internal execution engine, which is fast, scalable, and fault tolerant. We kind of talked about that this morning with some of the throughput numbers where we were showing how things like Tungsten and Catalyst and whole stage code gen can really make a huge difference in terms of streaming throughput. But even more important, I think, than the raw performance of the system is how quickly you as a user can take some problem that you have and express it using the APIs of the system. And so we have all of the high-level, highly productive APIs, DataFrames, Datasets, and SQL, all available for you as structured streaming. And then finally, we want to have tight integration with these ecosystem components. So I think one of the things that we did right with Spark SQL was the data source API. We want to build a similar system for sources and sinks with structured streaming. But really, at the core, what this means is when you're doing streaming computation, you shouldn't be thinking about streaming. That should be the job of the system. And so really the way that I like to think about this is you as the user write simple queries. You express the transformations, where the data is coming from, how often you want it output, and then Spark should figure out internally how to actually execute that in the best way. This is kind of very similar to the declarative processing ideas that really caused us to build Spark SQL in the first place. So to make this a little more concrete, I want to kind of talk about one specific use case, a relatively simple one, which is just streaming word count. And I want to walk you through the different parts of creating a streaming query that would answer this. So at a high level, this is pretty simple. I have a Kafka topic, and it just has words in it. And what I want the output to be is group by word and count. So just how many times does this word appear in the stream? So let's look at what it's like to express that kind of computation in structured streaming. So step one should look very familiar to users of Spark SQL. This is just like the data frame reader API, and this is how you load all data from different streaming sources into a streaming query. We just say kind of which connector we want to use. We provided options. In this case, we say we want to subscribe to one topic, which is the input, and we load it. We can load many different sources in a single streaming query and union them together. And I think that's actually pretty powerful. So the next step then, once we've got the data loaded as a data frame, that's kind of our skinny waste of computation in general, is now we want to do transformations. So this is a very simple transformation. It's just group by the word and do a count. And then I'm going to rename those two columns to be key and value so I can output them back to Kafka. So what's actually going on under the covers, though? Because as soon as I start talking about aggregations and other things, you have to kind of think, what is Spark doing? And I think this is an important part of understanding how the query planner and the optimizer are working. So you express some kind of computation using the DataFrame API. We can turn that into a logical plan, which just says kind of, at a high level, what sort of data flow do I want to occur? And then the optimizer actually figures out a way to execute that, doing things like using stateful computation, so propagating the information from last batches and things like that. And then we actually execute this individual query plan at different trigger intervals. So the next step now, now that I've loaded the data, I've done the transformations that I want, the next step is to say, where's the target? Where do I want to write this out to? And we call that a sink. Again, this should look very familiar to users of Batch Spark, because this is exactly like the DataFrame Writer API with just a couple of differences. So again, I specify which connector I want to use. I say where I want to write it out to. You can use both the built-in connectors as well as kind of create your own arbitrary connectors using the for each sink, which just basically calls into your user code for each tuple that the query produces. And for many cases, we can actually be transactional with our sink, which is pretty cool. So when you're writing to files, and eventually Kafka, once the transactional Kafka producer is out, we can actually do this transactionally as well. And then finally, we have to say, how do we actually want those answers to be produced? And so the important part here is there's two different parts. There's, what should I output? And so with any streaming query, we want to output incremental results as the computation goes on. And so we call this the output mode. So at each trigger interval, what do you want to be produced? The simplest one to think about is complete mode. It's exactly as though you had run a batch query at each trigger interval and return the entire answer. This is useful if I wanted to say, compute the top 10 web pages on my website or something like that, where I actually do want the entire answer to the query every round. Now, in some cases, that doesn't make sense. So like for this word count example, I actually only want to know the counts that are getting updated. So I'm running this query in update mode. And then finally, there's another mode called append mode, where it's very similar to update mode, but we actually promise that we're only going to add new tuples, and then we'll never change them. And so that's actually a property of the query itself. And TD is going to talk more later about how that works with watermarking and other more advanced features in structured streaming. So then in addition to the what output, we also say when to output, and that's called the trigger. You can specify that today as time, and I think it's likely that in the future we'll also add the ability to specify a data size. You can say trigger every minute or trigger every 100 megabytes, and that's like when it's actually going to produce an answer. And if you want to run with very low latency, just don't specify a trigger, and we'll continually execute batches as quickly as possible. And so then the final part is to actually start the query. And usually when you start a query, you want to give it a checkpoint location. The point of the checkpoint is for fault tolerance. So it actually tracks the progress of the query in persistent storage. And so if I restart a query using an existing checkpoint, it's going to pick up exactly where it left off, right before it failed. And I just want to go into a little bit more of the details of checkpointing, because this is actually quite a bit different than the checkpointing that users of dstreams are familiar with. Basically, like I said, it's tracking both the progress, so the offsets that have been consumed, as well as any intermediate state that exists inside of the query. And one of the cool things here is instead of using just kind of raw Java serialization that includes the query plan itself, we're kind of separating the computation from the progress. And what this means is that you can actually change the code to your streaming query, add another filter, things like that, and then restart it, and it will pick up where it left off with the new code. So this is great if you find a bug in your pipeline or the scheme of the pipeline changes. You can actually go and update it and restart it, and it will continue exactly where it left off. So that's kind of a high-level overview. To dive into some more of the details, I'd like to introduce TD, who's one of the core developers on the structured streaming team, who's going to talk about a bunch more features as well as some real use cases. Thank you very much.
Thank you very much, Michael, for the introduction. So So yeah, that was basically a 10,000 feet overview of what a streaming query in structured streaming looks like. What are the segments? How do you think about it in a holistic manner? But what I'm going to do is actually take a more specific, a more complex use case than counts and dive deep into how it actually works. And when you're writing the code, what does it mean when you're using data frames, and what are the properties of data frames? So a very common, or like one of the most common use cases of using streaming is doing streaming ETL. Now, ETL, or extract, transfer, loading of data, traditionally, the way it has been done is that there are streams of data coming in. What people traditionally have done is that they have dumped the raw data without any sort of processing into some intermediate files, because that is an easy thing to do. Dump it as fast as possible within seconds, and then run a periodic job every 6 hours or every day or every hour at best to take all the dumped files and kind of put it all into some database, SQL, NoSQL, in a more structured format so that you can now run more complex queries on the data. Which essentially means that the time taken to convert the raw data streams to actual structured data that is ready for consumption downstream for further analytics, there are hours and hours of delay. Which is fine for some use cases like reporting, dashboards, and stuff, but really not fine for use cases like where you want to do anomaly detection, you want to do intrusion detection where time is actually of essence. You want to catch anomalies and debug them and analyze them and do all sorts of things as soon as it happens, not hours later. The damage is already done. So the whole point of structured streaming is to enable things like streaming ETL, where we want to enable you to write applications where you want the data, that is the raw data from data streams, is available as structured data in some sort of table-like form within seconds. And I'm going to explain this with a more realistic example than word count. Let's say you want to essentially take data from Kafka. You have JSON data coming into Kafka. You want to read from Kafka. You want to parse the nested JSON and extract out all the fields from it, and then store the data in a more structured format like Parquet or ORC. And then also, obviously, you want to get end-to-end exactly one's guarantees because you don't want any data missing or you don't want to double count the data. To do that, all the code you need to write is this. So all this sort of complex parsing, JSON and stuff can be done very easily within structured streaming because of a lot of built-in functionality. I'm going to walk through this code line by line so that you understand that what are the things that are going on and how much power does this API has. So step one, you have to read from Kafka. And so the way it works is that you do spark.readstream, and you specify what is the format of this data source, which is Kafka. And you have to now for the system to actually read the data, you have to specify information like how to read, like which brokers to contact for reading the data. So you specify that. You specify that in the form of options. You specify what to read. Either you want to subscribe to a particular topic or subscribe to a pattern of topics, or you want to maybe actually read particular topic and partition for more intricate applications. And then finally, where to read from. So either you want to start from the latest offset or from the earliest offset or a specific offset for each partition. So you can specify all of this information as options. And then finally, you ask the system to load this information in the form of a data frame. So what you get at the end is this raw data frame, which essentially is equivalent to a table with the key and the value from Kafka as binary blobs. And you also get additional columns like topic, which topic it came from, which partition it came from, what was the offset and timestamp when it was recorded in Kafka, and things like that. Now with this tabular format of the data frame, now you can do more complex transformations. For example, I know that this data is essentially JSON strings, so encoded as binary. So first of all, I need to convert the binary to a string before I can do anything. So that's essentially step one in the transformation phase. So I basically am casting the value column as string and calling it and giving it the name JSON. Now that it is a string, now we have this inbuilt function called from.json. What this does is that it can take a string column and parse it, given a user-specified schema, to automatically split all the data inside the JSON into separate columns in the form of nested. So as you can see on the slide, a single JSON string column gets split into nested separate columns, and now you can do more complex operations now that it is separated into separate columns. But for now, I don't want to do more complex operations. All I want to do is ultimately save to a Parquet format. It's a very basic ETL. But now, to further simplify future operations, I don't want to keep it nested. I just want to flatten it out so that in future, I don't have to write very deep column names and stuff. So flattening it out is very easy. You just say data.star, and all the sub-columns will get flattened out into distinct columns. So the takeaway here is that what we use here is built-in functions that automatically did all this complex parsing and splitting and stuff. So this is the power of the Spark SQL engine and all the functionality we have added over the last 2-3 years. We can all use all of that functionality in streaming. And so you can do really complex stuff with very minimal lines of code once you can harness the complex functions that are already present, built into Spark SQL. And there's more information on these complex functionality in our blog post. So when the slide gets published, I highly recommend you to take a look at these functionalities. And then knowing these functions and being able to use them will make you really a superpower and will dazzle your engineer friends that, wow, I could do this sort of complex transformation in these few lines. So I highly recommend this blog post. And then finally, I want to write out to Parquet. So for that, you would want to specify the format as Parquet. And in addition, I know that in future, I'm going to query the data in Parquet by, let's say, the last hour or last 1 day or last 12 hours. So one convenient thing I can do is just partition the data by date. And so, which means that when I do interactive queries on the Parquet table, I don't have to read the whole table for last 1 year of data. I know that I can read only the files that are for the last 1 day because it is already partitioned by date. Then finally, we obviously have to specify the checkpoint, as Michael already told you. It's just a S3 or HDFS path, and call start to actually start the query. Now, you might be thinking that why are we considering Parquet at all? Like, I mean, this is a streaming system. We could write it out to Kafka as well and keep it in a purely streaming fashion. One of the biggest advantage of actually doing it not keeping it as a pure streaming thing, but writing it out something like Parquet is that it's much, much more efficient for any downstream computations. So the advantage of file formats like Parquet or ORC is that it will structure the data in such a way that you can do all sorts of query optimizations and file read, scan optimizations, file skipping, all sorts of query optimizations you can do based on the query whenever you are trying to interactly query it or run batch jobs on it. So, that is something that you really cannot do on a pure streaming storage system like Kafka. You cannot say that read only these columns out of the data, out of all the data, and you can do all of that in Parquet. So that means that you can, all your post-processing will be 10x more efficient if you have already encoded the data in a structured file format like Parquet, as opposed to keeping it purely in a storage engine. So that, and 10x lower cost means that you can run more complicated, 10x more complicated analytics within the same cost envelope. So that's why it's very common to actually take ETL out to something like Parquet or ORC and stuff. Anyway, so once I actually call start, now the system actually starts running the incremental query in the background on your Spark cluster, and it does all the logical plan, physical plan, optimization, tungsten, all of that crazy stuff we have been doing for the last 3 years. All of that kicks in. And what you get in the end is this query as a handle to the running query. And you can use this handle to actually do all kinds of management and monitoring of the health of the query. You can the query started, you can stop the query, you can see whether there was any exception, you can wait until the query finishes if it runs out of data. You can see what is the progress of the query by seeing that, okay, in the last batch, how many records were processed, what were the input rates, what were the processing rate, all of that you can use the handle to get all sorts of metrics and stuff. So now, as this query is running, data is getting written as Parquet files. So within seconds, your data from Kafka is available for your data analytics folks to immediately start running ad-hoc queries on that data within seconds. And this is why this is so cool. And another unique property which is special to Spark streaming, so to structured streaming, is that we preserve a very neat property where we ensure something called prefix integrity. And what it means is that as data is getting written out from Kafka to Parquet files in batches, we ensure that either you see all the updates from a batch in the Parquet table, or you see none of it. So so the updates are very transactional and atomic in nature, so that when you're running interactive queries on it, you don't get inconsistent results. Either you see all the results, all the updates after a batch has been processed, or you see none of it at all. And you can read again more about this in our blog posts. Highly recommended. Anyways, finally, in 2.2, we have added a lot more Kafka support. You can actually write out to Kafka directly. That has been a highly requested feature since 2.1. You just have to specify format Kafka again. And, well, you have to do write stream instead of read stream. And format Kafka, you have to specify which topic you want to write it out to, and start. And specify the brokers and start. You can also, and this is where it gets really fun, you can directly run batch queries and interactive queries on Kafka directly. So, which means that you don't even need an intermediate file system. You can use the Kafka as a complete file system, and you can directly run your interactive queries on Kafka. Even so, in cases like where your streaming application was down, you need to, for 6 hours, and you need to backfill the data in the middle because you don't want missing or holes in your Parquet files. You can do, this gives you a lot of power to actually start a streaming restart the streaming application from the latest data, but figure out what is the range of offsets in your topic that are still missing, that was not processed, run a huge backfilling bad job to actually fill that hole into the Parquet file. All of these things can be done because of this ability to directly run batch and interactive queries on Kafka directly. So, not just Kafka, we have also added support for Amazon Kinesis. This is a Databricks Runtime 3.0 feature, and it is already available on Databricks platform, so you can try it out, Kinesis, on Databricks. And the options are very similar to Kafka. You specify the how, what, and where to read from, latest or the earliest, name of the Kinesis stream, your region, AWS keys, etc. So, this was an overview of a simple, it does complex stuff, but still relatively simple map-only kind of streaming ETL queries. More complexity comes when we have to actually work with time. So the working with time specifically usually refers to working with event time. So that is the time that is present in the data itself. And you want to do windowing and complex analytics using the event time that is embedded in the data. And, common examples are, let's say you have your IoT devices and you want to monitor them to see that every 10-minute windows, what is the average signal strength and things like that. And this was one of the fundamental limitations of the old dstream API in the old Spark streaming. That API was not really designed to accommodate event time. And so the big advantage of structured streaming is that structured streaming has first-class support for building event time-based applications. Let's see how. So let's start with simple event time aggregations. So you want to basically count the number of events you received in last 1 hour windows using a field which is after parsing out all the JSON and flattening and stuff, there's a field called timestamp. And that is the time when the data was generated in your IoT device. And you want to basically count every 1 hour, how many devices reported their data. So the cool thing that we have done in structured streaming is that windowing is no different from grouping. It's just a fancier form of grouping. Essentially, you are kind of putting the records that you have received, looking at the timestamp and putting it into different 1 hour buckets. So it is a kind of grouping. And the way to specify this grouping is just simply group by window based on the timestamp column, 1 hour. It's very simple, verbose, SQL-like, so it kind of integrates naturally into the language. And you can write it both in DataFrames as well as SQL. And if you want to do more complex, like for every device, I want to get a separate count for over 10 minutes, or something like average signal strength over 10 minutes. That is also pretty simple. You can group by both the device and the window and average the signal strength. So, and for those who want to write more complex aggregations, it naturally supports UDFs. There's the aggregator API. There are a couple of different APIs inside DataFrames for you to express your own complex user-defined aggregation logic. So now, note that this is essentially a running aggregate. So if I do, let's say, just a count, I'm not getting the count of just each batch. I'm getting a cumulative count that is continuously being updated as more data comes in. And to do something like that, you essentially need to maintain state across the duration of the query. So the intermediate aggregates, the intermediate counts, those need to be essentially preserved in such a way, in a fault-tolerant manner, so that it doesn't, as soon as it gets new data, it can just update from the previous partial count to generate the next partial count. So this means that this intermediate counts need to be maintained within the Spark cluster as in-memory, distributed in-memory state. And each trigger, each time there is new data, the old intermediate state is read. New data is computed and added and updated onto the state to create the next version of the state, next version of the intermediate counts. And so all of this state is essentially stored in memory, but for fault tolerance, it is actually backed by any fault-tolerant file system like HDFS or S3 in a write-ahead log. And this is all done transparently by the engine. So the user doesn't have to worry about any of this logic. All the user has to write is the query semantic, the query on what you want to group and what is the aggregate you want to do. And this whole system is seamlessly fault-tolerant and exactly once. And the cool thing is that this naturally handles late data because you're maintaining these intermediate aggregate counts as state. If our data happens to come out of order and late, it automatically can be put in the right bucket, even though that is not the latest bucket being updated. That bucket still exists. So the late data can automatically be added to that bucket and counts updated. As you see in this example on screen, even if there is late data, older windows can get updated very seamlessly. And so the system will continuously maintain the correct count, even if there is no, the user doesn't have to do something explicit about late data. But a side effect of this is that the system does not know when it can throw out old state data, old aggregates. For example, your data is likely to be, let's say, not more than 1 hour late. So that means data that is 5 days old is not likely to change at all. You probably don't care about that data at all. So you really don't want to maintain that in the state, because the more state you keep, the more memory it eats up in the cluster. The more state management, the cost of state management increases as well. So what we can do about that is that in Spark 2.1, we have added something called watermarking that allows moving these old states to be gracefully cleaned off. And so let's define what a watermark is. A watermark is essentially a moving threshold of how late the data can be. And accordingly to that, the old state can be dropped. For example, let's say the max time you have seen in your data is right now 12:30 p.m. So the latest data is at 12:30 p.m. Your data can say, let's say, max 10 minutes late. So that means that if I maintain this threshold of 12:30 minus 10, 12:20, if I start ignoring any data that is marked as 12:20, then I can clear off any of the state related to that. I'm going to ignore any data that is labeled as 12:20 right now. And this, as the system receives new data, this threshold keeps moving forward, but always trails behind the max event time seen by the system. So that means that data can be late because it may be older than the max event time, but as long as it is still newer than the watermark, it will be considered in your aggregates or in any kind of processing. But if your data is so late that it is older than the watermark, then that data will be dropped. It's not going to be considered anymore, and its corresponding state, like for example the 5-day-old counts, are going to be cleared off completely. And this is how the system can control the amount of state it can keep. And this leads to a very nice trade-off that you can control. Depending on your application requirements, you can specify how much late data you have to consider in your system, and accordingly the resource usage will increase. So if you have to consider a lot of lateness, you have to consider that, then your resource usage will increase. But if you want to keep your resource usage down, then you have to do a trade-off in how late your data, your application is allowed to handle. So that is a very configurable trade-off, and the way to do that trade-off is by specifying this gap, this trailing gap behind which, based on which the watermark trails behind the max event time. So in this case, specifying the watermark in code is very easy. You just say with watermark, what is the event time column on which I'm going to actually read, I'm going to consider Git as the event time, and what is the delay, the trailing gap, the watermark is going to be behind the event time, the max event time. And note that this is, when you specify this additional operation, it is useful only in stateful operations like streaming aggregations. Other operations that are not stateful, like map or filter, will completely ignore this additional configuration. And if you run the same query after it's DataFrames, so you can run the same query on batch data as well. All batch and interactive queries will completely ignore this thing. So this is like a special optimization that is added to handle streaming applications only. So when the query actually runs, we are going to actually see that the system automatically figures out what is the max event time, automatically tracks it, automatically figures out that based on the trailing gap of the watermark, what is the actual value of the watermark should be, and accordingly some data may be late, but it will be considered, and some data, it is not too late, and so therefore will not be considered and its state cleared off completely. So what this formulation in the API results is that there's a clean separation of semantics. There is a query semantics that you can write, and it is cleanly separated in the API from the processing details, because you first, when you're writing a query, you first define what is it that you want to group. You want to group by how much time, etc. And this query semantics is exactly the same for batch and streaming, no matter what you run it on. But when you're actually processing it in a streaming fashion, you can specify these details, like how late the data can be and how often to actually emit the updates by writing the trigger. So at this point of time, I'm sure that some of you may actually want to take a break. This is a full 1 hour talk, but there's a break in the middle. So I think this is a good cutoff point where you guys want to take a break or go to a different session. So let's take the 10-minute break.
Yeah, we will take 10-minute break, reconvene here for those of you interested in continuing. Apologies for the delay, but there's no session after the next one, so we can run for as long as we like. All right, thanks, guys.